Assalamualaikum and a good day to my dear lecturer. My name is Akmal Hazim bin Mahuri from EE242 under supervision of Dr. Khairul Safwan bin Muhammad. Welcome to my presentation video. So today I'm going to present my final year project entitled Analytical Study of Zero Voltage Switching Bridgeless Boost Rectifier. So let's start to the introduction. Do you know what is the meaning of the zero voltage switching? Zero voltage switching can best be defined as the conventional square wave power conversion during the switch on time with resonant switching transition. For the most part, it can be considered as a square wave power utilizing a constant of time control which varies a conventional frequency or on time to maintain the regulation of the output voltage. For a given unit of time, this method is similar to fixed frequency conversion which is used as an adjustable duty cycle. Then, why are we use the bridgeless boost rectifier? This is because the most popular topology among the AC to DC converter and is offer a simple way to achieve high power factor and regulated voltage. So, what is the benefits of the zero voltage switching? Number one is to reduce the electromagnetic interface. Number two is to no power loss due to the discharging. And then the number three is high efficiency with high voltage inputs at any frequency. Next part is the problem statement. What problem that inspires me to do this kind of project? So here we have two problems that inspires me to do this kind of project. The first one is a conventional converter have a higher switching losses as the frequency increases. This is because in these topologies, regulator MOSFETs incur losses every time they switch. So a higher switching frequency leads directly to higher losses. These inefficiencies are primarily due to high side losses during turn on, million gate charge and the body diode conduction losses. To make things worse, conventional topologies further magnify the losses as higher impulse voltage are converted or regulated. And then the number two is the setting of the controller so the converter achieve lossless transition with the simple pulse width modulation control. Many soft switch converters have been discussed in the literature to address the additional stress imposed by the auxiliary circuits. For instance, the resonant capacitor is bypassed for a given time interval by using the FT switch. The output voltage can be regulated and controlled. So next part is the objective. What needs to be achieved in this project? In this project, the first one is I aim to study the operation of the current flow, zero voltage switching bridgeless boost rectifier. And then the number two is I aim to reduce the conduction loss in the auxiliary circuit. For the next part, let's see the methodology of this project. As you can see here, this is the proposed converter topology that I use in this kind of project. From the circuit, the first section is the power width modulation continuous conduction mode step-up converter, composed of a L-in, S1, S2, D1, D2 and the CO. The proposed circuit second segment includes a novel zero voltage switching bridgeless boost rectifier, auxiliary circuits that provide soft switching on all the semiconductors, the auxiliary diodes D3, D4, D5 and D6, as well as the resonant inductor LR1, LR2, the resonant capacitor CR1 and the auxiliary switch S3 are all rated for lower power as compared to the output power. The driving signals of both MOSFETs are the same in order to simplify the driving circuit. Both MOSFETs have identical driving signals. So to determine the transition states in the power conversion, we must know the current flow of the operation. For the stage 1, the main switch S1 and the auxiliary switch S3 are both turned off before starting, and the current IN flows via D1 and V out. This stage begins when turns on with the zero current switching at the T is equal to 0. The resonant inductor LR2 charges linearly from the output voltage V out. The resonance of LR1 and the CR1 increases both of the resonant current and resonant voltage. For the stage 2, the auxiliary circuit uses CR1, CR2, LR1, D5, LR2, D3 and S3 to provide a continuous resonant behavior. This stage ends when the resonant voltage reaches output voltage. Next, in stage 3, this stage begins when the resonant voltage is equal to the output voltage and the body diode of the main switch turn on at the zero voltage switching. The resonant current is maintained at the value ILR2 in this stage because the freewheeling loop and the body diode of the primary switch S1. This stage ends when the sum current of the resonant currents is equal to the input current again, and the body diode of the main switch S1 naturally closes at the zero current switching and zero voltage switching. During stage 4, at T is equal to T3, both the resonant currents flow through the main switch S1, and the body diode with the zero current switching goes off. And at zero current switching, the auxiliary switch S3 is switched off and the diode D3 is naturally closed. In the stage 5, this stage begins when the auxiliary switch S2 turns off at the zero current switching. The resonance begins by the way of CR1, LR1, LR2, and the D5. After that, during stage 6, when the diode D5 shuts off the zero current switching, this stage starts. Through primary switch S1, current I-in continues to flow. The rest of the semiconductors are turned off. The last stage is during the stage 7. The input current flows through the D1 and load. This stage ends at T is equal to T7, when the main switch S1 is gated onto the start the next operation period. As you can see here, this is the main waveform for the simplified zero voltage switching bridgeless boost rectifier. During stage 1 and stage 2, we can determine there is no conduction loss at the waveform VDS1 and IS1 because there is no intersection between those waveforms. Next part to the simulation result. The software development that we use in this project is a PSIM. PowerSim is a market-leading provider of simulation and design tools for power electronics. This software specializes in the research and product development of power supplies, auto drivers, power conversion, control system, and microgrids. So, this is the proposed converter specification that we use. For the input voltage, we use 230V RMS because we follow the Malaysia standardized AC voltage. For the output voltage, which is 450V DC, while the input frequency also follow the Malaysia standardized AC voltage, which is 50Hz. Next, switching frequency use 5000Hz. Next, this is the proposed converter parameters that I use in this project. So, this is the circuit topology that we propose in this project. Down below, here it is controller that we use the open loop strategy because it is easier for us to troubleshoot the controller. Next, to run the simulation, this button is pressed. Now, we choose the waveform Vin and the Vout to determine the input voltage and the output voltage respectively. The waveform of the input voltage and of the zero voltage switching bridgeless boost rectifier at the 325V VP to peak. This is because the conversion from the VRMS to VP to peak. Then here the output voltage converted from AC to DC at 450V DC. Next, for the waveform VDS1 and IS1. At the variable available, we choose the VDS1 and then IS1. But for the IS1, we multiply by 10 because we want to zoom in the waveform. Okay. The previous waveform we delete because we want to show the commutation at the VDS1 and IS1. So here we can observe that there is no intersection between both waveforms. The simulation demonstrates that the zero voltage switching are achieved at a constant frequency for active switch and auxiliary switch. Therefore, the switching energy losses for this new zero voltage switching bridgeless boost rectifier are practically zero. Okay, the last one, we want to show you the resonant waveform of the inductor and the capacitor. First we choose the ILR1 and then ILR2. And then click the VCR1 for the resonant capacitor voltage. As you can see here, this is the waveform of the resonant inductor current and the resonant capacitor voltage. For the last part is the conclusion. In the conclusion, a new zero voltage switching bridgeless boost rectifier auxiliary circuit was presented to achieve 7 transition states in the power conversion, and then the conduction loss in the auxiliary circuit can be reduced by optimizing the turn-on time of the auxiliary switches. Thank you for listening to my FYP presentation. I hope you guys have a blessing day. So, Assalamualaikum and bye bye.